Um, may I take off the mask or? Okay, today I talk again about my project, which we will put on the archive probably tomorrow. So, yeah, I don't want to repeat the presentation from last time, so I will focus on the things that have been added. But let me first just explain to you the general idea of the quantum Doppler radar. So first of all, Doppler radar tries to estimate the velocity of a moving object, as can be seen here. And first let us look at the classical version of this Doppler radar. So we have the radar here, and this radar prepares a probe state, a classical probe state, which we choose to be a coherent signal or a laser beam. And this probe state is sent to the target of interest, which is moving with a constant velocity. And there it interacts with this object. In this case, it's just reflected and the frequency is shifted according to the Doppler effect. So, and this interaction can be described with a unitary transformation. And this transformation imprints this parameter lambda, which is related to the velocity onto the state. So then after this interaction, the third step comes. We have to collect the probe state and then measure it. And here we have the freedom of choice, which measurement to take. Obviously, we want to use a measurement that is advantageous for us, so we can get a lot of information with as little resources as possible. So the measurement then gives us a number or maybe multiple numbers, and those numbers then can be analyzed and can be used to make a guess about the parameter. So that's the last step. That's the last step, the data analysis. So that's how this quantum radar protocol works. And in our work, in our project, we want to look at the quantum version of this radar. And for this, we use an additional beam. And this beam shares some entanglement with the signal beam, and we expect that this can enhance the sensitivity of the protocol. So let us now look more into the details of this quantum probe state. So we chose a generalized version of the two-mode squeezed vacuum state, and this state is probably the most commonly created states in quantum optics laboratories. So that's a good thing because people can create this state. And also it's a Gaussian state, so there are a lot of analytic formulas for Gaussian states, and this can be used to ease the calculations. So let me tell you how you can create those states. First, we have some pump beam, which is a coherent state, a classical state. And this state interacts with this medium, a nonlinear medium. And there, those pump photons, some of them decay into two photons. which we call the signal and the idler. And due to energy conservation, the energies of those signal and idler photons have to add up to the pump photon frequency. So, and this enforces frequency entanglement. So, yeah. So naturally, in the state creation, we already have entanglement, frequency entanglement. And so the state, if we write it down, it looks like this. We treat this problem in a continuous manner. So we have to integrate over the frequencies of both of the photons. And here we see the squeezing parameter, which is one of the resources of our quantum state. And then we have the frequency entanglement, which we cannot see directly how big it is, but it is contained in this function f of omega omega tilde. And if we can write this as a product function, then there's no frequency entanglement between the photon pairs. And if it's really hard to write this as a product function, then this decomposition here has a lot of terms. And the number of these terms, so I mean we can do a so-called Schmidt decomposition of this function here. And if there are many terms, then that means we cannot really write it as a product. And the number of terms is called k, which is the Schmidt number. And the larger this k, the bigger the frequency entanglement. So those are the two resources, k and the squeezing xi. And now we want to compare this quantum protocol with the classical protocol and see if there's an advantage and how does this advantage behave by varying our quantum resources. And also how does it depend on the photon number, which is always an interesting variable. So how can we evaluate the performance of the protocols? There is a theory called quantum estimation theory, and there the main figure of merit is the Fisher information. And the Fisher information just tells us how much information we can extract about the parameter that is encoded into a quantum state. So this is the state, and then we have a measurement. So we have the state and the measurement, and then we have a formula, and this tells us how much information we can extract. So if this Fisher information is big, then that's good. We can get a lot of information. And if we maximize the Fisher information over all the possible measurements, then we get the quantum Fisher information, which is the ultimate precision limit. And yeah, we are interested in this ultimate precision limit first to see what can we achieve in the best case scenario. And also the good thing is that it's really easy to calculate because it only depends on the derivative of the state, but not on the optimal measurement itself. So to calculate it, we don't even need to know what is the optimal measurement. But obviously, we are also interested in the measurements, and we will talk about this later. So, but first, let us just talk about the optimal scenario. So we assume to have a quantum Fisher information, other thing. Yeah, and here I just wanted to show you the result of the calculation. It's a pretty messy formula and cannot really, I mean, it's not so intuitive. So the goal was to first try to find some approximations so we can understand this better.
What is the parameter that you estimate?
Yeah, we estimate this lambda, and this lambda is related to the velocity of the object. Yeah. So, yeah, this is the result of our calculation for the quantum state. And now we want to analyze this in different parameter regimes. So yeah, first of all, the classical strategy, that's pretty straightforward. We find that the quantum Fisher information is just proportional to the number of photons. And this is called the standard quantum limit. So no classical strategy can be better than this scaling. And in the quantum paradigm, we can have a quadratic improvement compared to the classical case. So we have quantum Fisher information that's proportional to n squared. And yeah, in this diagram, you see the quantum Fisher information of the quantum protocol for the parameters. So we plotted against both quantum resources. So here is the squeezing, and here is the frequency entanglement parameter. And we see three distinct regimes. So three different behaviors for different parameter choices. So for example, here, this red area is the area where we have a lot of frequency entanglement, but not so much squeezing. The squeezing is here, and we don't have so much. So this is what we call the high entanglement regime. And there we find that a scaling of k times n. So we still have this scaling proportional to the number of photons, but we have an enhancing factor of k, and this k can be really big. This could be 400 or something like this, so it could be really big. So here in this regime, we have a big quantum advantage. Yeah. And then here the high squeezing regime. So we don't have so much frequency entanglement, but a lot of squeezing. And there we find this scaling. So we have n to the power of 1, and then plus some term that's larger than 0. So we have a scaling above the standard quantum limit, and thus achieve a quantum advantage. And here in this white area, we kind of have both frequency entanglement and also squeezing, and they are somehow comparable, or at least, yeah, both quantum resources contribute equally. And here we find that the quantum Fisher information is proportional to n squared, which is called the Heisenberg limit. And that's the typical quantum scaling for quantum metrology protocols. And that's, yeah, a nice advantage here. And yeah, one of the things that I've worked on is just to try to find those approximations. And last time I didn't know how to come to this approximation, but now I found a way. So yeah, okay. But here we just can even show it just by plotting the quantum Fisher information. Yeah, okay. So those are the quantum advantages. And now, last time we were not so sure about what to measure. So that's obviously a big question. It's nice to have the advantage, but if you cannot achieve it because you cannot perform the optimal measurement, then this quantum advantage isn't really useful. So there's one optimal observable which is given by this formalism of quantum estimation theory, and we can easily calculate this optimal observable. But the problem with this one is that we don't really know, or at least I don't know, how one could measure this thing in a laboratory. Yeah, the structure is quite complicated. And another problem is that this observable depends on lambda, on the parameter itself. So to construct it, you need to know the parameter. And I mean, that's not a huge problem because you can adaptively construct the measurement. But I mean, in practice, it would be still challenging. So, and yeah, we also looked at this special case. Yeah. So in the pursuit of finding the optimal observable, I looked at this state, at the few photon case. So in this regime, we only have a small number of photons. So the state can be approximated just as the vacuum plus this 2-photon state. And because the structure is so simple, we can easily calculate the Fisher information for a given measurement. And we decided to look at the measurement of the photon frequencies. So the photons are detected and the frequencies are also detected of those photons. And what we found is that this measurement is optimal for this specific regime. But it wasn't clear if this measurement is also optimal for all parameter regimes. So we knew for this special case, this is an optimal measurement, but is it also an optimal measurement for all parameters? So that was the thing to investigate. And yeah, so the question was, is F equal J? And yeah, because you have to calculate infinitely many integrals, we had to come up with a more general way of looking at this problem. So we proposed 3 conditions for a measurement and then showed that if a measurement satisfies those conditions, then the Fisher information is equal to the quantum Fisher information. So those are the 3 conditions. Those POVM operators should be one-dimensional projection operators. They shouldn't depend on the parameter itself. And the amplitude should be real. And if you use these 3 conditions, you can, in the definition of the Fisher information, you arrive at this result in the end. And yeah, we see, okay, it's equal. And this frequency resolved photon counting satisfies those conditions, so we know this measurement is optimal. Yeah, so this was one more detailed excursus. And yeah, another thing we considered was loss. So the problem is once you have loss, the state turns into a mixed state. And with a mixed state, the quantum Fisher information is much more difficult to calculate. Probably there's a way, but we don't know yet. But yeah, so what did we do? We modeled the photon loss just as a beam splitter, where the probability of losing a photon is just this eta. And then we calculated a lower bound for the Fisher information, one that is easy to calculate. Because the full calculation, yeah, we don't know how to do it yet. And yeah, this lower bound is really, really pessimistic because we only take into consideration the measurement runs where no photon has been lost. So, I mean, when we have loss, there's a chance that no photon gets lost, and we only look at these instances. And with this, we can calculate this lower bound for the quantum Fisher information. And here we just look at the ratio of the quantum lower bound Fisher information and the classical strategy. And if we are above this line here, above the dashed line at 1, we have a quantum advantage. And yeah, at this left part, we fixed K and we fixed the frequency entanglement and the squeezing and varied the loss parameter. And for zero loss, we are in the lossless case. So we start out with a pretty high advantage. And as we increase the loss parameter, we see that the advantage decays. And yeah, the more photons we have, the more rapidly this advantage decays. And then in the second diagram, we fix the loss parameter to 0.7. So 70% of losing a photon. And we vary the frequency entanglement. So we start with 0 and end with 60. And we see that this quantum advantage scales approximately linearly with the frequency entanglement. So even if we have a really high loss or a really lossy quantum channel, just by increasing this frequency entanglement, we can achieve eventually the advantage. And this is what we see. I mean, with the blue line, we get there pretty quickly. But with the red line, which is a photon state with more photons, we need a much higher frequency entanglement. But
how do you explain physically? Because theoretically, the larger the spacing, the larger the entanglement. So why you achieve or you can get a better behavior for lower spacing and for light?
Okay, I mean, in this regime, the squeezing is directly related to the number of photons. So, so the number of photons is given by chi squared. So if we have lower squeezing, we also have fewer photons, and the fewer photons we have, the better it is, due to, the nature of our lower bound. I mean, the lower bound only considers measurement events where no photon has been lost, and if we only have a small number of photons, then the probability that no photon has been lost is higher than for a higher photon state. If we have 10 trillion photons, the chance that we lose at least one photon is 1, essentially. So, I mean, yeah, it just has to do with how we derive this lower bound. And this lower bound favors states with not so many photons. That's the point, yeah. Oh, okay, yeah, and that's all. Okay. Yeah.
Quick question. Did you assume a beam splitter with where you regulated the transmittivity for the low photon?
Yeah, I mean, what do you mean with regulate the transmission?
Yeah, so you're not using I mean, this is on paper, but you're not using a 50-50 beam splitter. It's a beam splitter where you regulate how much passes through, right?
Yeah, no, it's not a 50-50. We can freely choose this parameter. I mean, this is how we model the photon loss. And it's not that we have in the experiment a beam splitter somewhere. We just model the loss as a beam splitter. Yeah. Yeah.
A is the when you in the beam splitter when you put the A is the quantum operator or because what is A exactly? Because if you have a beam splitter in the quantum and you want to work with the beam splitter in a quantum way, you have to take in account the vacuum. You cannot only use three like so you are using operators you want to use with the beam splitter in the quantum regime. I was reading the other day that you should use you have to take in account the vacuum like an operator like the four beam.
Yeah, we also have this fourth beam, this vacuum here. But yeah, usually if you want to consider also thermal noise, then
Yeah.
That's
Right,
also
right.
important. But I mean, yeah, I mean, in this figure, I've just shown it like this. But yeah, you also have this fourth
Okay.
port, or yeah.
And this is for you. There you are the thermal noise and you can add the thermal noise and everything that no.
Yeah, yeah. This is, I mean, we assume here that the vacuum enters, but later we will consider thermal noise as well.
Okay. What happens when you fix in the second block? If you fix the eta to 70%, what happens when he or she tends to zero? Following your
I mean, this
your
line
reason.
probably will go like this, but
But in zero you have no state. So
yeah, if we have no state, then it's nothing. But
so still your image of why this road is not convincing.
I mean, yeah, I mean the smaller the xi, the higher the slope. And but yeah, for c equals 0, then we have nothing. Then we just have 0. Oh, no, but also for the. But I mean, we also. Oh yeah, I think it would just approach like infinity or this line, because we also reduce the photon number in the classical strategy as we decrease the xi. Yeah.
Would you expect the optimality of the measurements that you brought before to change very little with small changes to lambda, to the parameter that you want to estimate? If I understood correctly, you mentioned that you have to construct the measurements with some knowledge of the parameter you want to estimate, so you expect there will be some error in the estimation, right? So do you expect with small changes to the parameter you want to estimate, the optimality of the measurement to not change? I mean, or the shape of the optimal measurement?
Yeah, I mean, for this frequency resolved photon counting that we propose as an optimal measurement, there, I mean, this measurement doesn't depend on lambda, so there we don't have this problem. But if we have an operator like this, then yeah, it's difficult to say how sensitive this observable is with respect to small changes in the lambda. So yeah, I mean, I've read some paper for another protocol where they did this optimal or adaptive measurement strategy. And
but in general, for parameter estimation, in the theory of parameter estimation, you have to know the prior value of lambda. So when you try to distinguish between lambda 0, let's call it lambda 0, and lambda 0 plus delta lambda, it's what you solve. Then you have to know about lambda 0, and it's what you need here also.
yeah, I guess we need to know our probe state. So we need to know this omega 0, or at least the mean frequency of the probe state, to detect the shift. Yeah, so in that sense we need to have prior knowledge about the parameter. Yeah.
But this happens always with parameter estimation, so it's not problematic. You can obtain some information about the prior value by a classical method. Let's calculate it, and then what you are trying to do is to improve this value using the quantum protocol.
I mean, we want to measure this frequency shift due to the Doppler effect, so in order to estimate the shift, we need to know the frequency before the reflection. But, I mean, this shouldn't be a problem.
What do you mean by optimal observable? I don't get the point, and also, does it matter of optimism? So optimal means that you can approach your quantum feature information with the least gap or with the largest sensitivity.
Yeah, so, okay. So if we just take some arbitrary measurement for a particular probe state, we get the Fisher information that's generally smaller than the quantum Fisher information. But an optimal measurement is a measurement where the Fisher information is equal to the quantum Fisher information. So yeah, this is what we mean with optimal. And then was there anything?
I mean, your we check your measurement and sensitivity, so that your measurement result is approaching the limit of
Yeah. I mean, with this one particular measurement of frequency resolved photon counting, we get this Fisher information that is equal to the quantum Fisher information, to this thing here. And I mean, then in the last step, this is just a measurement, and then we have this last step of analyzing the data. But that's never a problem. If you only have one single parameter to estimate, then there is an estimator that can estimate this parameter optimally, given a high enough number of experiment repetitions. Yeah.
What is your initial state?
My what state? I didn't.
Is that a state involved? You choose your initial state, so this must be must have some influence on your measurements.
Yeah, I mean, we create the state, and then during this propagation, the state also evolves.
Sure.
And due to this evolution, we get those phase factors, but the measurement that we chose is insensitive for these phases. So it doesn't matter. The phase or this evolution due to the propagation has no effect on the measurement data. So our measurement is phase insensitive, and yeah, so yeah, but there are, I mean, in principle, one could use also information that is encoded in the phase of the state. But yeah, here we chose to just look at the spectral properties of the beams, and yeah.
Any other question? No? Okay, let's thank again Mark for the papers. Anyone?